Hi everyone. So in the last class we looked at the principle behind nozzles. We saw how the velocity of a fluid, with emphasis on gases, the velocity of gases increases at the expense of pressure, meaning as the velocity increases, the pressure decreases. So we'll be looking at a couple of examples just to reinforce this. Let's The question says air at 860 kPa, so that should be our force pressure, that is P1, and 190 degrees C, that should be at C1, expands and at the rate of 4.5 kilogram per second. So we are seeing something pointing to velocity already through a convergent divergent. And if you remember, we said convergent means that things are coming together. So convergent divergent. So we have this point of so this is the convergent point of the nozzle, and this would be the divergent point of the nozzle. So we have those 2 points, and then we know that the middle part will be the throat, where choking takes place, into a space where the pressure is 100 kPa. So you can see already the pressure, the incoming pressure is high, the the exit pressure is low. So that will be our P2. Assuming that the inlet velocity may be neglected, calculate the necessary throat and exit cross-sectional area. So we are looking at the area at this point and at the cross-sectional area at that point. So those are the 2 areas we are looking for. And we've been given those values. So typically what you want to do is first put down everything you've been given, and then based on that you'll be able to know. So you want to take note of the known values, the unknown values. So the first thing, known values, unknown values, and then you want to look at the appropriate formula that connect what you've been given. Remember, another thing you always need to take note of is consistency of units. Consistency of units. So one thing to get all this right, it's another thing to get that right. If you get all this right and you get this wrongly, at the end of the day, it's still going to give you wrong answer. So having said that, we know that the ratio of the pressure at the section where sonic velocity, we know this is at the throat. So sonic velocity is achieved at the throat. Remember, you start from the subsonic. Subsonic velocity happens here. Subsonic velocity happens here at the entrance, and here sonic velocity happens, and at the exit we have what we call supersonic velocity. And remember, we also talk about how m be less than 1 here, which is the Mach value. M equals to 1 at the middle, and m is greater than 1 at the supersonic point. So we've taken note of that. Another thing we talked about in class is it's at the sonic point, which is at the throat. That is where the critical pressure, critical temperature, that is where you have all those occurring. So everything, all the critical values will be achieved at the throat. So let's look at what we have. So the P1, we have that. We've converted for consistency. We've converted it to Newton per meter squared. We have the mass flow rate, m, specific heat ratio of air, which is your gamma. So take note of that. Gamma is same as your specific heat ratio of air. And we have our gas constant, which is 287 Newton meter per kg per Kelvin. So just for consistency, we've done that as well. So we move on as we have the CP value, which is a constant which will always be given. So we have our CP value of air also has also been provided. So to calculate the throat area, this is what we're looking for. The question says we should remember the question is the throat, calculate the necessary throat and exit cross-sectional area. So our first, everything that happens in the throat is here, and this is where we'll have the critical pressure, critical temperature, and critical velocity. So I haven't noted that. It means that we can use this formula, which you'll find in the lecture, in the chapter 16 lecture slide 7. So see lecture slide 7. So you see this formula there. So you see this formula there. But always take note, critical pressure and every critical pressure occurs at the throat. So if this is the critical pressure, this would be our inlet pressure. And then we have all these other values. Our gamma value is given. So we just need to plug that into what we already have. So if we plug that in, we arrive at this. So that's it. So it's about identifying the appropriate formula and then plugging it in. So the next thing we want to calculate is the critical temperature. Remember, all we've been given, we were given the inlet pressure, inlet temperature, and inlet temperature. We are looking at the critical values. So similar to what we did there, also you see this in slide 7. You see this equation in slide 7. So similar to what we did for pressure, you plug in the appropriate values, the inlet pressure here, the inlet temperature there. If we plug everything in, we have our critical temperature. I want you to also take note of the sequence in which these questions are typically solved. So we started with the pressure, we moved on to the temperature based on what we were given, and then we are moving on to the volume. Take note of that. Another thing I want you to take note of is that the inlet is always our reference point. So we start from the inlet. So that is our reference point. So I haven't said that we can use, remember, your ideal gas relationship of PV equals RT. That will always hold. So if we know our P, we know our T, we have this, which is a given constant, and then we can find our V. So that is what we've got here. That is our volume. So we have our PV and T. PV and T. Moving on. This is another expression that is also given in slide 7. So in slide 7, which gives us the critical velocity. So take note of that. So critical velocity is C. So we've calculated the critical pressure, critical volume, critical temperature. Now we are calculating the critical velocity before we can get to the cross-sectional area. So we use this formula that has been given again. You have it in slide 7, and then we have the critical velocity. Remember, because of the consistency of the unit, we were able to get something with the value of meter per second. This is another one you find in another equation you're going to find in slide 5. But remember where we are going. We are looking for the area, the cross-sectional area at the throat. And we've said that will be a critical volume. So critical area rather. Everything happening at the throat everything happening at the throat is critical. So we call them critical values. So if you plug that in, I hope you see why we had to go through that route, because we needed the VC, we needed the CC before getting here. We were given the M already. Remember, we are given the M in the question. So we just plug that in. We've calculated the VC, we've calculated the CC, and then we have the cross-sectional area. So this is our cross-sectional area at the throat. Remember, we said it's at the throat that the velocity becomes sonic. It's at the throat that the velocity becomes sonic, and it's from that point that supersonic velocity starts generating. So that's why it's a critical point. So similar to the approach used to solve question 1, remember 2 questions we were asked to solve: cross-sectional area at the throat and now at the exit point. So similar to the approach we used to solve 1, and at that point we were also focusing on, at that point, remember, we focused on the for the first part, we focused here on the convergent part. So now to calculate the exit value, the cross-sectional area at exit value, we'll be focusing at the divergent point. So we've seen at the convergent. Now let's look at the divergent point. Let's look at the divergent point. So we follow the same step, because remember, we need VC, we need CC for us to get the AC. That's one. And also remember, we said our reference point is always what? P is always P1. Your T1, your reference point, is at the inlet. So you see that we're still using similar formula that we've used earlier. So T1, but this time around we are no longer using critical values, because this is at the exit point. So it's at the exit point that we are looking for values now. At the exit point we're looking for the cross-sectional area at the exit point. We know the P value at the P2 rather at the exit point. So it's at the nozzle. We've done the nozzle already. This is where we have the PC, the TC, and the CC. So here we are going to VC. So at this point we'll be looking for the P2, T2, and then we'll be looking at all those other values. So similar, we follow the same route. So we follow the same approach right from the beginning to the end. So we calculate the T2 from the PV equation, we get the V2 there, and from this other equation we get the C2. Can you see the same root? And then we get the A2. So if you have to compare, so I want you to compare this 4867 millimeter squared, compare it to that 2788 millimeter squared. So you should the reason why I'm showing you that is you should always be able to make sense of your calculations. It's not just about calculating something. You should be able to know its implication. You should be able to see, does it make sense? Because it wouldn't make sense if something we've called convergent divergent, and then you're showing if the divergent value were to be smaller than the throat, that means something is wrong somewhere. But looking at this, you can see the divergent value is higher than the throat, the cross-sectional area, the throat at the cross-sectional area. And also I want you to also take note of other values too. Let's have a quick look at the speed. Look at the speed here, 650. You remember we said the pressure should decrease. The pressure should decrease, but the velocity should increase. Let's see if that is obvious here. C2, 650.5, and CC, can you see there, 393. So take note of that. So the area has increased, the velocity has increased. So this further shows that yes, indeed, we are working with a convergent divergent nozzle. Convergent divergent nozzle. So let's look at another example, 6.2. Example 6.2. The question before we look at the. Okay, so the question is written here. So let me just quickly, So it says gases expand in propulsion nozzle from 3.5, and so as we saw previously, this will be P1, and so this will be T1, down to a back pressure. So we see this is P2 at the rate of, so we have the rate, the velocity, taking a coefficient of discharge of 0.99, that our gamma value, and the nozzle efficiency. We know what nozzle efficiency is, of 0.94. Calculate the required throat and exit areas of the nozzle for the gases. For the gases, this is coefficient of discharge. We have that formula, and this, take gamma should be here, and CP should be here. Assume that the inlet velocity is negligible. So please take note of what we are given. So let me just take that off. Yeah. So that is the coefficient of discharge that we are given there, and these are the other values that have been given. So let's go back to, based on what we were given, let's go back to look at the appropriate equation. So we've been given the P1. We've been given the P1 value. We have the T1 value. Remember, always convert to Kelvin. For consistency, because we were looking at speed in meter per second and other things, as we see, as we move on, we'll see we've converted to Newton per meter squared. And mass rate, we are given kilogram per hour. But for consistency rate, we want to convert it to kilogram per seconds. So that would be 64800 kilogram per second. Remember, 60 minutes make 60 minutes make 1 hour, and then we know 60 seconds make 1 minute. So 60 divided, so that's how we got that. So kilogram per second. Coefficient of discharge, we are given 0.99. Nozzle efficiency 0.94. So already you're beginning to see, what equation will be appropriate here. Specific heat capacity of gases, that's also given. Specific heat ratio of gases, that's a gamma value provided. Similar to what we did in the previous calculation. Let's first calculate the values at the throat. So we know, since we have the value at the inlet, we can calculate the value at the throat, and then we can move on to calculating the value at the exit. So what are the values at the throat? Critical values. So we have a formula as we did previously. Plug everything in. So remember, P1 is always the reference point. So remember the approach from previous the first question. We said we look at, if once we have P, we should be able to look at the T value, and from the PV relationship, we should be able to calculate the volume, and from the volume we should be able to calculate the velocity. And once we know the velocity, we should be able to calculate the area. These are some of the logical things we will see as we so you should be able to understand this logic. So for example, this can either be meter squared or millimeter squared. Here we are dealing with meter per second. Remember, volume, meter cube. So you should be able to follow through or see that. All right, so we know this already. Plug everything in. We have our TC, and then so we have our TC. We weren't given R value, so we can calculate that. We have the R value there. Remember, the question gave us CD, coefficient of discharge. We were given coefficient of discharge, but unlike the first question, in this particular case, we weren't given MS. in the first question we were given ms, but in this one we weren't. So if we use what we have, this, we've seen this, you see this in the lecture slide. If you plug that in, then we'll be able to get our ms value. So we've gotten that value, and then from there we want to be able, using the PV relationship, we can calculate our VC. Remember the root T, we have the P, we have the T, look for the V, velocity, and then look for the area, look for the V, and then, so we have the V, we have the velocity, and then now we have the area. But remember, we weren't given this, we calculated this from there using the coefficient of discharge. So that's how we got that. But you see, it's the same logical route that we used earlier on that we've also followed through here. And remember what we said earlier on, check if it's convergent, divergent, 33,900 millimeters squared. That is the AC, that is at the throat. So we'll see at the exit if it's lower or bigger. So same logical route, we follow the same thing to calculate at the exit. So basically following the same thing what we did in question 1. What we did in question 1, we're following the same thing, and we are using all the values that were given to calculate what we don't have. So you see this in slides 9 and 10. Look at these equations in slides 9 and 10. So we have this already. So T, we've seen this already. So the T values, and then we want to calculate the T2. So this is our T2. So T2, remember, that is what is happening at the exit. Once we have T2, we can calculate the V2. You can calculate the V2, so which is there, the V2. So we have our V2, we move on to C2, and then eventually get to the A2. Let's see, what did we get for the AC? Critical area, 33,900. Here, 42,200. So you can see it's greater. Let's look at the velocity, 632 meter per second. And what is the velocity, critical velocity? Let's go back. C2 632, critical velocity 470. So you can see it's also higher. So those are some of the things you want to always cross-check when you do such calculations, just to see if what you're doing is making sense or not. So so that's where we're going to stop for this particular chapter 16. As usual, if you have queries or anything you'd like clarity on, don't hesitate to send me a message on Telegram or WhatsApp, or send me an email. All the best. Cheers.